Cool. So welcome everyone to the last day of the workshop. So we have an exciting schedule for this morning. We'll start with Daniel Kane from UCSD, who is going to tell us about some joint work with Elias Diaco-Nicolas. Take it away, Daniel.
Okay. Hey, yeah. So I'm going to talk to you today about small covers for near zero sets of polynomials and learning latent variable models. This is all joint work with Elias Diaco-Nicolas from UW-Madison. So let's start with a basic problem. Let's look at learning Gaussian mixture models. So X here is a mixture of K, let's say spherical Gaussians in Rm. So you've got some number of means mu I and some weights wi, and you pick one of these means with probability proportional to its weight, and then you return a sample from the identity covariance Gaussian with that mean. And so the problem we're going to look at is given sample access to such a mixture X, we'd like to learn the distribution X. And so Gaussian mixture models are one of the oldest and best studied latent variable models in all of statistics. And it might be slightly more natural to look at mixtures of arbitrary Gaussians rather than just spherical ones that we are considering here. For the case of arbitrary Gaussians, there are m to the k lower bounds, at least in the statistical query model, which suggests that it's hard to find good algorithms there. And so hopefully in this model, we'll be able to find algorithms that are somewhat better than that. So there are a couple of different things that we might mean when we talk about learning this model. And the strongest of them is parameter estimation. What we'd like to do is we'd like to estimate each mean mu I and each weight wi to some error epsilon, and then we'll know the parameters of the model to good accuracy, and we can do everything else. And there has been some work in this area that says, well, okay, so if you have this mixture, if you assume that all of the weights are at least alpha, and you assume that the means are pairwise separated by something like square root log 1 over alpha, then there are algorithms that run in time quasi-polynomial in m over alpha. Now, the lower bound on the weight is, it's essentially necessary so that you can guarantee that you'll actually see samples from that component, but the separation is a little bit less natural. Unfortunately, something along this line looks like it might be necessary. There's a paper by Regev and Vijayaragan which proves that parameter estimation in polynomial time is actually information theoretically impossible unless you assume some kind of similar looking separation assumption between the means.
Wait, what does it mean, information theoretically impossible in polynomial time?
So in polynomial numbers of samples.
Okay, that's what you mean. Okay.
Yeah, so in polynomial numbers of samples, it's information theoretically impossible. And so parameter estimation is doable in quasi-polynomial time, but only if you make some kind of separation assumption along these lines. So the other thing that we might try to do that works more generally is density estimation. Here, the goal is just to learn some distribution x hat such that the total variation distance between x and x hat is at most epsilon. And as is often the case, this is at least possible information theoretically. It's now known that approximately mk over epsilon squared samples are both necessary and sufficient in this model to learn things information theoretically. However, algorithmically, all of the best algorithms for this problem have runtime that's still exponential in k. And so the big question that we're going to be trying to ask is it possible to close this gap? There's an exponential gap between the upper bounds and the lower bounds here. What can we do to improve this? And the general strategy that we're going to work on here is the method of moments. So we're going to try and compute the low degree moments of this mixture X, and then we're going to use them to learn the full distribution. And so before we get into this too much, we should ask ourselves, what are the low degree moments of this mixture model X? Well, if you just want the expectation of X, well, it's a mixture of components. So by linearity of expectation, what we should get is we should get the mixture of the expectations. So we just get the sum of wi times mu I. For the second moments, we look at the expectation of the second tensor power of x. And here we need to know the second tensor power of this Gaussian with mean mu I. And there we get the second tensor power of mu I plus the identity. And when you sum this up, you'll note that the identity terms sort of come out of the sum, and you get the sum of wi mu I tensor to the 2 plus the identity. And conveniently, this identity term sort of acts as just an extra factor that you can take out. And this sum of wi mu I tensor to the 2 is really the useful information to get out of this. And more generally, it's not hard to show that learning the first d moments of x is essentially equivalent to learning what I'll call the parameter moments of x, which is the sum I going from 1 to k of wi times mu I tensor to the d. These are basically the moments of the distribution that's just the distribution over the centers of these Gaussians and not the more general Gaussians themselves. And so this is what you can learn with moments. The question then is, given these values or approximations to them, what can we expect to do with learning the actual distribution? So how do we make use of these? And here's where we run into our first big obstacle. And the problem is that moments alone are not enough. It is not very difficult to construct two mixtures of k Gaussians, say x and x prime, even in one dimension, so that the first k minus 1 moments of x agree with the corresponding moments of x prime. And additionally, the total variation distance of x and x prime is large. In fact, you can construct this so that none of the means of one distribution are close to any of the means of the other distribution. So there's just some explicit families that you can pick. And if you only compute k minus 1 moments, it's not possible to tell which of these two families you have.
And when you say large, you mean how does it scale with k?
I mean, you can actually make them arbitrarily far apart. If you take whatever means you have and you multiply them by any constant, they're still going to match moments with each other.
Yeah, I get it. Okay.
Yeah, so there's an unbounded distance that you can have. In practice, if you make the means too far apart, there are some simple things you can do to cluster them. But you can make them close enough, they're not easily clusterable, that they're still going to be far apart. However, in one dimension, this isn't so much of a problem. In one dimension, you can always solve the problem exhaustively. You can sort of say, well, Gaussians in one dimension are close to piecewise constant functions if you make the pieces small enough. And you can just discretize the real line and just learn the distribution over this sort of discrete intervals. And it's actually not that hard. However, things become a bit more complicated when you take this one-dimensional example and embed it into a higher number of dimensions. You take literally any line that you like in this higher dimensional space, and you place means along this line in the same way you would have for this one-dimensional example. And once again, you can find a moment matching distribution, now in a higher number of dimensions. And so the problem is that if you want to distinguish between these two mixtures, you need k moments, and to compute k moments, even to write them down, it's going to take m to the k time. However, this case that I wrote down is still easy. So let's think about this second parameter moment matrix, which we know how to compute, or approximately at least. This is m, which is the sum of wi times mu I transpose. And you'll note that the image of m is the same as the span of the mu i's. Now, the construction that we looked at, all of these mu i's lie on a line. And so their span is one-dimensional or maybe two-dimensional. And by computing this second parameter moment matrix, we can find that one or two-dimensional subspace. We can project everything onto it. And once again, once you're in finitely many dimensions, there are basically exhaustive techniques that you can do that now work in polynomial time. And so for this problem, at least, it's actually not hard to do that. this technique is actually reasonably well known. I mean, generally you can reduce your m-dimensional problem into a k-dimensional problem using techniques along this line. And this is a fairly commonly used pre-processing step for problems like this. However, we now just need to find a slightly harder counterexample where this doesn't work. Because the example that we had, the algorithm that we were just talking about using is fairly brittle. It only works when all of the points lie in a low-dimensional subspace. So to fix that, we'll start with this low-dimensional construction that matches moments. And we're just going to add some extra components. These purple components, are in both the red distribution and the blue distribution. And if we just add a bunch of random components, it's no longer the case that all of our means lie in a low-dimensional subspace. So we can now find mixtures of, say, 2k Gaussians, so that these two different families, x and x prime, may match k moments with each other. And furthermore, the means from each of these families spans a k-dimensional subspace. So dimension reduction will only get you down to k dimensions. And then in order to distinguish these two guys, you need to take k moments. So what can we hope to accomplish then with method of moments? We can't hope to identify all of the individual components of x and x prime with just a few moments. But maybe what we could hope to identify is maybe we could identify these sort of noisy components that we added in to increase the dimension. And then once we've identified those, we again can't identify the individual components of x or x prime because they do match moments with each other. But maybe we can identify this line that all of the other components lie on. So the hope is we can identify the sort of straggler random guys and then the line where sort of this interesting moment matching construction is taking place. And hopefully we can do something sort of exhaustive on that line and have identified everything else. Okay, so this is sort of our goal, but the question is how might we be able to do this? And in order to get an idea for this, let's take another look at how this dimension reduction step works. So we have the second parameter moment matrix M. And you'll note that if for some vector v, you look at v transpose mv, this is the sum of wi times v dot mu I squared. And you get this interesting thing that v transpose mv here is going to be 0 if and only if v dot mu I is 0 for every I. And what this will allow us to do is, if you look at the subspace of v's for which this holds, then this will give us a big subspace of v that are orthogonal to all of the mu's. And in particular, like this is exactly the subspace of v's that are orthogonal to all the mu's. It'll be a k codimension k subspace because we're only imposing k linear conditions on it. And then if you look at the subspace orthogonal to that, you'll get a k-dimensional subspace which contains all of the means mu. And so sort of once again, we have this dimension reduction idea. But this sort of formulation is maybe a little easier to generalize. So let's think about what happens if we have higher moments. Suppose that we know all of the parameter moments of degree up to 2d. Well, one way of interpreting this is it means that for any polynomial q of degree at most 2d, we can compute the sum of wi times q of mu I. And in particular, we'll run the same trick that we did before. We're going to let p be the square of a degree d polynomial. So we have a quadratic form, which takes in a degree d polynomial p, and outputs the sum of wi times p squared of mu I. What you'll note is that q of p is 0 if and only if p of mu I is 0 for every one of the means I. And if we can get this quadratic form, we can compute the 0 subspace. We note that each of these p of mu I being 0 is a single linear condition. So we have a codimension k subspace within the space of all degree d polynomials, such that these polynomials vanish on every single one of our means. And okay, so we have this big vector space V. It's codimension k within the space of all degree D polynomials, such that P of mu I is 0 for every P in V and for every I going from 1 to k. So what does this tell us about where the means lie? Well, this set of polynomials defines a variety, defines the set of joint zeros of these polynomials, and all of our means lie in this variety. Now, for sake of intuition, let's bring out some very basic algebraic geometry. The dimension of the space of degree D polynomials on this variety is just going to be the codimension of V within the space of all degree D polynomials, and that's at most k. On the other hand, this is at least D plus the dimension of the variety, choose D. And a little bit of algebra says that the dimension of this variety V is therefore at most D times k to the 1 over D. And the hope is that somehow we've reduced our problem to working on this variety V of small dimension. And so hopefully, once we've made this reduction, exhaustive algorithms should take time now that is only exponential in D times k to the 1 in D. And I should note that, the D equals 1 case of this is exactly the dimension reduction to idea that we had before. We've got a codimension k subspace within the space of linear polynomials that vanishes on all of our points. And so this defines a k-dimensional variety, but since it's defined by linear polynomials, that means it's just a subspace. So we found a k-dimensional subspace on which all of our points lie. And then we have exhaustive algorithms that run in time exponential in k. Okay, so yeah, when D is 1, we've just reproduced the dimension reduction idea. But unfortunately, doing things for higher degree polynomials is not as straightforward. There are a bunch of obstacles. So the first one is just that everything I did on the last slide assumed that we knew all of the moments exactly. And of course, the best we could hope to do is approximate these higher moments. And that's still enough to approximate this quadratic form Q and find an approximation to the subspace V. But if you then try and compute a variety just from approximations to the correct polynomials, you're going to get garbage. They're going to have no joint roots, and it's not going to work. So we need to find a way to make this algebra work with approximate polynomials. Secondly, even if we had things that were exact, computing this variety might be difficult. With linear polynomials, if you have a system of linear polynomials, it's easy to figure out what the subspace they define is. For higher degree polynomials, computing and writing down the variety they define is not necessarily easy. And even if we could write it down, working on this variety might be difficult. For a subspace, we could just project all of our points onto that subspace, and it's not hard to see that that just reduces the problem to a lower dimensional version of the problem. With a more complicated variety, it's not clear what kind of projection onto the variety you're supposed to be looking at. It's not clear what exactly that means for the problem. Maybe it distorts things somewhat. It's much harder to work with. And finally, we run into this issue that maybe even if the dimension of this variety is small, it might still be very complicated. Maybe it's a one-dimensional variety, but it's some kind of almost space-filling curve. And just knowing that all of our means lie on this curve that basically goes everywhere is maybe not very useful to us. And so these are the problems that we need to solve with our technique. And the basic idea of how we're going to solve it is, instead of working with this variety directly, we're just going to approximate it by a comma. We're going to approximate it with a discrete set of points that we can work with. And so the tool that makes this all happen is the following technical lemma, which says that, okay, so V is a subspace of codimension at most k within the set of all degree D polynomials in Rn. We've got some parameters, epsilon, r, and delta, that have some relation to each other. And we're going to look at this set S. It's the set of all x in Rm that have L2 norm at most r, so we need to restrict this to a ball, such that for all polynomials in this set V, the absolute value of P of X is at most delta times the norm of P. So basically, we won't have all the P's vanish exactly on these points, but they're going to nearly vanish on these points. And given this, we claim that there exists a cover of S by balls of radius epsilon. And the size of this cover, the number of balls in this cover, is at most m, which is 2r over epsilon dkm to the O of d squared times k to the 1 over d. And furthermore, we can actually compute such a cover in time polynomial n. So basically what we're going to do is we're going to approximate this variety that we have by this union of balls. And a few comments about this. Firstly, we had the dimension of this variety was d times k to the 1 in d.
A question, you don't care about you didn't specify the norms that you're choosing for V?
I have not specified the norm that I've chosen for the polynomials. It doesn't really matter very much since different natural norms will only change by something like an m to the d factor, which somehow has already been sorted into how small delta needs to be.
Right, yeah.
But yeah, I mean, just using like the L2 norm of coefficients or something is good enough.
Okay.
Okay, so, but why do we expect something like this to be true? Well, if this was exact, the dimension of this variety would be at most d times k to the 1 in d. And so you expect that if you're covering a manifold of that dimension with balls of radius epsilon, you should have a cover of size approximately r over epsilon to the O of d times k to the 1 in d. And so our bound is a little bit worse than this. We have an extra factor of d in the exponent. We have some extra polynomial factors in the base. But morally speaking, this amounts to more or less the same thing. We have a requirement on delta, that delta is less than something like epsilon over r to the O of d. And something along these lines seems to be necessary to ensure that the width of the set S is at most epsilon. Because even if S approximates a low dimensional variety, if its width is more than epsilon, it's going to be hard to cover by epsilon balls. And finally, we don't have time to go into the proof here in much depth. What I'll say is that the proof is essentially elementary. It doesn't use anything complicated from algebraic geometry or anything. It just uses some clever recursions, a bunch of linear algebra, principal component analysis, things like that. But it is quite involved. It's not a simple proof, but it is an elementary one. But okay, so given this, how are we going to use it? So we want to learn this mixture of spherical Gaussians. So firstly, we reduce this problem to k dimensions using the basic dimension reduction that we've already talked about. The next step that you need to perform is you need to cluster the points. There are some relatively easy things that you can do to sort of reduce to the case where all of your means have absolute values, say polynomial in k. Next, we're going to let delta be, say, epsilon over k to some large multiple of d. We're going to compute the first 2d moments of x to error something like delta over 4, delta to the 4 divided by k to the O of d. And from that, we can compute the first 2d parameter moments to error, say, delta to the 4th. From this, we define our quadratic form. Q of p is approximately this sum of wi p of mu I squared. And we're going to let v be the span of all the small eigenvalues of q. And what's not hard to see is that if you have any mu where the wi is reasonably large, it's going to be approximately 0 for every p in this subspace phi. And so we're going to define S as before, and we note that for each I where wi is reasonably big, the corresponding mu will be in this S. And applying the proposition, we compute a cover C for this set. And now we know we've got this explicit set of points such that for every I where the weight is at least, say, epsilon over k, mu I is within epsilon of some element of this set. Now, how do we deal with this? Well, if we want to do density estimation, we note that if we take each of these mu's and round them to the nearest element of our cover, well, all of the reasonably heavy mu's, they were only moved by epsilon. And so we've only changed the distribution by epsilon. So in particular, our original distribution x is O of epsilon close to some mixture of NCI distributions where C was in our cover. And so what we have is we have an explicit set of distributions, and we have sample access to some x which is close to being a mixture of these explicit distributions. And it turns out that that problem is actually reasonably easy to solve. Basically, you can compute a maximum likelihood estimator for x as being written as such a mixture. And the analysis is not very difficult to show that this actually converges. And so the theorem is that if you have a mixture of k spherical Gaussians in m dimensions, you can learn it into error epsilon. Well, you need poly m over epsilon time and samples to reduce to k dimensions. And then you need something like k over epsilon to the O of d squared times k to the 1 over d time and samples to solve the problem after you've done that reduction. And setting d equal to log k, this gives us quasi-polynomial in k over epsilon. And recall, though, that previously the best known algorithms for this problem ran in time exponential in k. So we haven't quite gotten things down to polynomial, but we have made an exponential improvement over what were previously the best algorithms for this problem. Now, for parameter estimation, things were already pretty good, but we actually still get some improvements. So we still need to assume some sort of separation assumption. So let's assume that, the mu I, mu j, they each differ by about square root log k pairwise, and that we have this cover C. Now, there are some basically known techniques that allow you to do parameter estimation given this in time polynomial in the size of the cover, basically by using the cover to do clustering of points. And so the theorem is, given a mixture of k evenly weighted spherical Gaussians, where we've got this separation of square root log k, there's an algorithm that takes poly m over k plus k to the d samples. This allows us to compute the first d moments, and then runs in times poly m over epsilon plus k to the O of d times k to the 1 over d, and learns each of the mu i's to error epsilon. Now, what's the point here? If we set d equal to log k, this basically recovers the previous results, that in quasi-polynomial time and samples, learns the means to error epsilon. However, if you take a smaller value of d, this gives you a trade-off between the sample complexity and the runtime. If we're willing to take, k to the 100 samples, then we have runtime that's exponential in k to the 1 in 100. And so previous works could give you some sort of qualitatively similar trade-off, but they could only do it if you assumed a stronger separation. In order to get this kind of sample complexity runtime trade-off, previous works require that the means be separated not just by square root log k, but by k to the 1 in d. And so this technique allows us to get the full trade-off with only these sort of information theoretically minimal separation assumptions. Okay, so this is what we've attained for mixtures of spherical Gaussians, but if you think about it, this technique is actually far more general. For a pretty big sample of latent variable problems, you can follow sort of the same idea. You first learn the parameter moments of the model by taking samples. You then use this structural result to go from having parameter moments to computing a small cover of the set of parameters. And from there, you can run some sort of algorithm that's exhaustive in the size of this cover. And in particular, we have new results for learning positive linear combinations of ReLUs, learning mixtures of linear regressions, and learning mixtures of hyperplanes. And so to quickly look at a couple of those, so there's the sum of ReLUs problem. So you have f of x, it's a function of the following form. It's the sum I going from 1 to k, ai times the maximum of 0 and x dot wi. This latter function is a ReLU, and this should be for some non-negative numbers ai and wi's of L2 norm equal to 1. Now, what your algorithm is given is it's given samples x, y, where x is, say, a standard Gaussian, and y is equal to f of x plus some independent noise. And the goal is to learn an f tilde that is close to the original f in, say, L2. Now, what was previously known about this problem? Well, I have a previous paper with Ilias and a couple of his students that basically says that, well, we can compute the first 2 parameter moments in this model. That allows us to reduce decay dimensions, and then we can do a brute force search there. And so we get some runtime that's polynomial m over epsilon, but then exponential in k. Well, that's if you only computed 2 parameter moments, but if you're willing to compute logarithmically many parameter moments, you can use an algorithm very similar to the type we've talked about, and you get runtime and sample complexity poly m over epsilon plus something quasi-polynomial in k over epsilon. The other problem I'd like to talk about is mixtures of linear regressions. So here what you have is you've got some beta i's in Rm and some weights that add up to 1. The algorithm gets samples xy, where x is a standard Gaussian. And, well, what you do is you randomly pick one of the betas with this, according to this distribution, and then you set y is equal to beta I dot x plus some noise. Now, so if you just had a single beta I, this would be a linear regression problem. But because we have, a random, we pick a random beta I, we have a mixture of different linear regressions. And there are several goals you might have, but a natural one is to try and just learn the distribution over pairs xy to error epsilon. Now, here there actually is some notable past work. There's a paper by Chen, Li, and Song, which solves a sort of similar problem in this vein, in time polynomial in m and exponential in square root k. And this is pretty substantial. It still improves over the earlier work, so the runtime is exponential in k rather than its square root. However, once again, using these ideas, you compute the parameter moments of this distribution, you use it to get a cover, you then do something exhaustive. You need to pull out some tricks here to sort of cluster the points and do something iterative, but you end up with an algorithm for learning these mixtures with runtime and sample complexity that's polynomial in m log 1 over alpha over epsilon, and quasi-polynomial again in k over epsilon. And so once again, we have sort of an exponential improvement over other known algorithms for this problem. And so in conclusion, we've developed a few things. Firstly, we have this new structural result. It says that if you have a bunch of polynomials and look at the set of near zeros of that collection within some ball, that actually has a relatively small cover by epsilon balls. This gives rise to a new algorithmic technique where if you can compute these parameter moments, you can use the structural result to find a small cover of the set of means. And from there, you can use exhaustive techniques that often lead to quasi-polynomial time algorithms for a pretty substantial number of problems. And finally, we have specific applications of this technique. We have the first sub-exponential time algorithms for learning density estimation for mixtures of spherical Gaussians, learning positive linear combinations of ReLUs, and learning mixtures of linear regressions. So yeah, that's all I had to say. Are there any questions?
Great, thanks a lot. So I have a quick question. The algebraic geometry result that you use on the dimension of the variety, is it Alexander Hershowitz or is it something more elementary than that?
I guess I don't know the names of the results. It's been a while since I took an algebraic geometry class.
Oh, okay, no problem. But okay, but this is tight. This bound that you gave for the dimension.
The bound of the dimension of this variety is tight. In particular, if you just take a subspace of that dimension and then look at all the polynomials that vanish on the subspace, I mean, the codimension of the set of polynomials will be exactly d plus the dimension of the subspace.
Yep. So then my next question is, so what we expect is in the dimension of the cover, I mean, the size of the cover is to have something which is exponential in D, not D squared.
Yeah, you expect it to be only D rather than D squared. And the proof technique for this proposition gives D squared. And it wouldn't be surprising if there was an improvement, but it took enough work to get what I had that finding this improvement that, would improve your algorithms from, k to the log squared k to k to the log k didn't seem worth it.
Right. And also, because the dimension is tight, it means you cannot go beyond quasi-polynomial with this technique, right?
The technique as it currently stands is generally not going to be able to give you better than quasi-polynomial because, yeah, d times k to the 1 in d can't do better than that. There is maybe some hope of being, the dimension should continue to shrink as you make things bigger. D to the times k to the 1 over d is not necessarily a tight bound. Really what you should be looking at, and I have to go way back to find this, was this bound that k is an upper bound on d plus the dimension of the variety choose d. And this actually should give you something slightly better than d times k to the 1 in d.
Oh, I see. Yeah. Yeah.
On the other hand, quasi-polynomial is still a natural barrier because if you have to compute all of the moments up to degree d, you have this extra factor in your runtime that's already going to be something like
right.
And so I have a few ideas on how to get around that potentially, but without some substantial improvements to this technique, quasi-polynomial is going to be a barrier that's hard to beat.
Great. Thanks a lot. Any other question? Okay, we're already running 5 minutes late, so maybe let's end here. Thanks a lot, Daniel.
Okay, sure.
And Shai, if you want to share your slide.